So hi, in today's lecture we are going to see that how to find the peak element. Now the peak element is an element which is strictly greater than its neighbors. Okay, so they are giving us an array in which we have to return the index of the peak element. Okay, so talking about the condition. Okay, so see, if a of I minus 1 is lesser than a of I, and this element is greater than a of I plus 1 as well. Okay, so we found our peak element, so simply return I. Okay, so I believe you got the question. Now in the question they are also giving us that to imagine a of minus 1 and a of n is minus infinity. Okay, so in other words, an element is always considered to be strictly greater than a neighbor that is outside an array. Okay, so the element present at minus 1 is infinity. Also the element present at ninth index is minus infinity. Okay, now if I convert this array in a form of chart, so it will look like this. Okay, now over here we can simply see that this is nothing but a peak element because the neighboring elements is lesser than this. This is also a peak element. Okay, so here also we can see that there are two peak elements. Now we can return any of them. Okay, so finding a peak element in an array may look like a coding exercise, but in real life it is how we detect peak in stock market, ECG signals, or even the highest mountain in a terrain maps. Okay, now let's see that how we can solve this problem. But before that, let me also tell you that in this lecture I am going to burst a myth that the binary search can be only applied on the sorted array, which is wrong. Okay, so in this today's lecture I'm going to show you how. Now the first approach will be, as usual, the brute force approach. Okay, so we know the condition, right? So the condition is a of I minus 1 is lesser than a of I, and this element is also greater than a of I plus 1. So I'll just simply have AND condition in which a of I is greater than a of I plus 1. That's it. So we know the condition. Now what we can do, we can just simply have this condition in every values. Okay, and whichever value is satisfying this case, okay, we can simply return the index. But this condition will be failing on these indexes. Why? Because if you're standing over here and if you want to know the value present at a of I minus 1, we don't have this value, right? So this will be failing. Similarly for this as well. So what we can do, we can just simply have if a of 0 is greater than a of I minus 1. Sorry. Okay, if this is the case, then we can simply have return 0. Okay. Similarly, if value present of a of n minus 1, if it is greater than value present at n minus 2, then we can simply return n minus 1. Okay, so we don't have to go further. Now we will be having one simple for loop in which I will be coming from 1, I will be less than n minus 1. Okay, I plus plus. Now we are going to have this case if a of I minus 1 is lesser than a of I and a of I is greater than a of I plus 1. Okay, so we can simply return I. And that's it. We are done. Okay, now talking about the time and space complexity, here we can see that we have just taken one single for loop. Okay, so the time will be order of n. Okay, And talking about the space complexity, since we didn't take any extra space, so it will be constant, so order of 1. Okay, and this line and this line will be going to take constant amount of time. Okay, so I believe you got this. Now in the question they are asking us that we have to write an algorithm in which the time complexity should be order of log n. Okay, so how can we solve this? So approach 2. Now let's see that if you're standing in the middle, okay, in which the value present at a of I is 9. Okay, the value present at a of I plus 1 is, let's say, 5. Okay, and the value present at a of I minus 1, let's say, is at 12. Okay, this is I minus 1, this is I plus 1. Okay, now if you are standing over here, okay, and if we decided that the peak value is present on the left hand side, okay, we have just decided. Okay, so let's see whether our decision is right or wrong. Okay, see, if I go on the left hand side, okay, the value present at a of I minus 2, okay, might be greater than this 12. Okay, let's say 15. Okay, or the value present at I minus 2 can be lesser than 12. I hope you got this. Okay, so let's say this is 8 and this is 15. Okay, if the value present at I minus 2 is 8, okay, then it means that this is the peak element, so we got it. Okay, but similarly, let's imagine that we are going on the right hand side, okay, on this. So here also we will be having two cases in which the value present at I plus 2 is greater than 5 or it is lesser than 5. Let's say if it is greater than 5, so this will look like this, and if it is lesser than 5, this will look like this. Okay, so let's imagine that the value are, this is, let's say, 8 and this is, let's say, 3. Okay, in both the scenarios this 5 can never be the peak, right? But in one of the cases, okay, this 12 is turning out to be a peak element when the value present at I minus 2 is lesser than that. Okay, so here there is a chance, okay, that this might be the peak element. So based on that only we can go on the left side. Okay, so taking this observation, what we can do, if a of I minus 1 is greater than a of I, then go left hand side. If a of I is lesser than a of I plus 1, that means the right hand value present on the right is greater, so go right hand side. And there is one more condition. If a of I minus 1 is lesser than a of I and a of I is greater than a of I plus 1, then simply return value the index sign. Okay, now since we are going on the left or on the right, okay, so here we can apply the binary search approach. Okay, but before doing that, there are some cases that if we check, then within a snap we can get the answer. Okay, the conditions are, if the length of an array is 1, in that case we can simply return 0th index. If the length of an array is 2, okay, then here we can have the if cases, basically a ternary if. So a of 0 is lesser than a of 1. That means here in this case the a value present at a of 1 is greater, right? So return 1 or else 0. Okay, but let's say what if the length of an array is not 1 nor 2? Okay, here also there are two cases. The first cases will be if a of 0 is greater than a of 1. Okay, so the value present at a of 0 is peak, so return 0. Similarly, if a of n minus 1 is greater than a of n minus 2, here also we can simply return n minus 1. Okay, now we are going to have the while loop for the binary search approach. So low will be 1, high will be n minus 2. Okay, because for 0 and for n minus 2, for 0 and for n minus 1 we already have the condition. While low is lesser than equals to high. If this is the case, first we need to find the mid. So int mid is equals to low plus high minus low. Okay, this is another formula for finding the mid, okay, in which this formula works on the larger data set. Now after finding the mid, we need to check if a of mid minus 1 is lesser than a of mid and a of mid is greater than a of mid plus 1. If this is the case, then we found our peak, which is a mid only. So we have to return mid, but the mid value is not peak, so we have to have another condition. If a of mid minus 1 is lesser than a of mid and a of mid is also lesser than a of mid plus 1. So here in this case we can see that the mid plus 1, the value present at mid plus 1 is greater. Okay, so we have to go on the right hand side. Okay, so what can we do? Since we have to go on the right hand side, go right. So the low will be mid plus 1 and at last we can have the else case, in which here we have to go on left. So since we have to go on the left, so high will be mid minus 1. That's it. So I believe you got this. And at last we can just simply have return minus 1 just for the formality. even though this line will be never going to execute. But for the formality, we have to have this line. Now, I believe you got this. Now this for line will be going to take constant amount of time, right? Talking about this while loop, since here the binary search is actually happening, so the time complexity for this will be order of log n. Okay, and the space complexity, since this is an iterative approach, so this will be constant. Okay, so I believe you got this approach, okay, which was quite of a different one. Now the thing is that even though the array is not sorted, okay, then also we have applied binary search approach. Okay, so applying binary search approach only on a sorted array is false. Okay, we can apply, but it depends upon the questions. Okay, so I believe you got this. I'll see you in the next lecture. Till then, keep practicing. Thank you.